Welcome! If you saw my last video, back. If you didn't see it, we explored how fractals like this can be generated by imaginary number systems, such as base 3i. And there's a lot more to this topic, so now it's time to spin the GrayCuber sequel wheel! What'll it be? Let's wait and see! Make the viewers uncomfy. Hey, this is a bad idea. Everyone's gonna hate that knocking sound. Yeah, you're right. Let's move it over. We'll add an extra dimension. Can we find a way to turn these 2D fractals into 3D fractals? Well, this idea can be viewed from two different perspectives: algebra or geometry. With algebra, we have a base and some digits, which we use to write numbers. With geometry, we have a grid that contains a pixelated shape. Both sides are currently at
Level 3.
I'll show you how we can upgrade them. For geometry, this shape has a transformation rule and a replication rule. So to upgrade, we just apply each rule. And then in algebra, we have 3-digit numbers, and we can upgrade them by multiplying by the base, then adding a digit to get 4-digit numbers. So now both systems are at
Level 4.
And if we apply those rules again, then they upgrade to
Level 5!
Now remember, each side is just a different perspective of the same system. They're linked by the imaginary numbers. Multiplying an imaginary base will apply the transformation rule, and adding imaginary digits will apply the replication. What's with the static? Hey, the wheel hung. Right, we want to add an extra dimension. Last time we used two-dimensional numbers. Each value had a real part and an imaginary part. So now maybe we can add a whimsical part. Although, disfortunately, that would break these links. 3D algebra can't model 3D geometry. Well, this link still works. If we have some 2D numbers, their locations make a 2D shape. The replication rule turns every single square into that shape. And we can just do the same thing in 3D. But what about the other link? On the algebra side, we multiply by the base. 0 times the base should be 0, and 1 times the base should be the base. Geometrically, we want a transformation that will fix 0 and move 1 to the base. To do this, we can rotate the grid until they line up, and then stretch the grid until they match. Now let's try this in 3D. We can rotate until they line up, and then stretch until they match. Did you notice the problem? Yeah, me neither. It seems like that works. So let's apply it. We'll pick a base and some digits, then start with a shape at
Level 1.
We can apply the transformation and apply the replication to get to
Level 2.
Then apply them again for
Level 3.
As we continue, a fractal emerges. Let's start over with a different base and digits. As you can see, this process can make cool shapes. But it only uses geometry. When we try to link to algebra, we run into 3 problems. First, my logo will interrupt this explanation. Second, the transformation is not unique. Remember, we want 0 to stay fixed and 1 to go to the base. If we pick a base, then we can rotate and stretch to meet these requirements, but then we can apply an extra rotation around 0 and the base. This still meets the requirements. So to be specific, we need to pick a base and an angle for this extra rotation. Then throw in some digits, and this uniquely defines a fractal. And now watch as we change that extra angle. We get this cool morphing effect. It's really fun to watch, but it introduces our third problem. The cubes are going inside of each other. Maybe we'd want to find fractals where they line up nicely, without touching. And this is really easy if we switch from geometry to algebra. The imaginary I is defined as squaring to -1. This is an That's short for integer. And it means that imaginary algebra preserves All of the form a grid. If we pick 2 then their sum will be and their product will be And so if we use an base and digits, then their fractal is... Oh, looks like it's time for a hydration break. Everybody have some water. Oh, sorry, I got distracted. We want to add an extra dimension. So if we change this definition and say that I cubes to -1, then we end up with 3D numbers. Every value has a real part, an imaginary part, and an imaginaginary part. We can add numbers like this, and we can multiply them like, no, make it go away. We'll make the computer do all the math. But we should notice that the definition uses an So imaginaginary algebra preserves If we pick an base and digits, then we get nicely arranged cubes. And if we base and digits, why is it glitch? Why is it glitch? The wheel glitch wheel. I guess we'll change the rules of the system. Well, we could change the I definition. Instead of I cubed equals -1, we could set it to -2, or -I. Or I squared plus I plus shooter. The wheel again? Wait, make the viewers chumpy? Chumpy? Why are chumpy? I guess we'll play with shapes. Well, last time we didn't just have squares. We also made fractals using hexagons. We can model the hexagons by starting in a square grid and taking just this checker interested. Points that are both odd or both even. If we squeeze them a bit, we get a hexagonal pattern. So we can pick a definition, a base, and digits. Then we get a hexagonal fractal. And of course, we can change the digits, or change the base, or change the definition. Wait, maybe we can't. They're overlapping. These values are hexagonal. They're both odd. But their product is hexagonal. It has odd and even. This definition preserves but it does not preserve hexagons. So how do we preserve the bestagons? Well, 1 plus I has both odd, so it's hexagonal, and so its square should also be hexagonal. That's 1 plus 2i plus I squared. Notice that this is odd and this is even, but they need to match. So the I squared should flip one of them. We must define it as either odd plus even I or even plus odd I. These definitions preserve hexagons. And we can take this idea to 3D. If we make a 3D checker interested, then the space is filled by these shapes. This is a rhombic dodecahedron, or ambido for short. These ambido are defined as having an even amount of odd values. So maybe they have 2 odd values, like 1 plus 3i, or 6i squared plus scooter I minus I, or instead they could have 0 odd values. We can use ambido to make some cool patterns, but they can have the overlapping problem. Here we're setting I cubed equal to 1 minus I. That's 2 odd values. Remember, the ambido have an even amount of odd, such as this. But substituting I cubed turns the even odd into odd. To preserve even odd, this odd should remain odd, such as odd even odd even odd, or odd. Oh, and by the way, ambido has a friend, the truncated octahedron, which we'll call aaron. Aaron fills the space where values are all odd or all even. And this means that the variety of aaron fractals is limited. And we need to be more careful about overlap. In order to preserve aaron, I cubed must be even odd or odd even. And check this out. These definitions preserve ambido. Odd even works for both of them. And it also preserves the cubes, so this is like a universal definition. For example, we could say I cubed is -1 plus 0i plus 0i squared. It's just the basic 3D I. And I think that really goes to show how funny life can be sometimes. Thanks to the recent supporters of the channel. Follow the link below to my open processing page, where you can play around with the code behind these 3D systems. We are killing the planet.